sigma alpha equals A alpha, then what you get is a Lagrangian goes to the Lagrangian plus A alpha. Let me get the d beta d alpha beta. So that's one way of getting the energy momentum tensor. And why am I saying this? Because we have the energy momentum tensor, but there is another conserved, so there's another conserved current, which is a conserved current when you do supersymmetry transformations. And that conserved current is called J. And it's going to give us more constraints. It's a fermionic, worksheet fermionic operator. So J is a conserved current. Under SUSY transformation, and this you can check. Let me write it here. So if you do a SUSY transformation as written there, what you get is actually that the Lagrangian goes to the Lagrangian plus epsilon bar d alpha J alpha. So it changes by a total derivative, the Lagrangian. And J alpha is -1/2 d beta x. Let me write the mu indices. X rho beta, rho alpha, psi mu. So it's a fermionic current. This is a vector index, but because of the psi mu has a spinor index, so psi mu is a column spinor with two components. This has two components. And it mixes the x's and the psi's, as one expects from being a supersymmetric current. So it's easy to show if you plug in the rhos that there are only two independent components of this. And you put this column spinor, only two independent components. Which are J minus, so this index alpha being a minus, and the index of the mu, so the fermionic index being a plus. So this is the worksheet vector and spinor index, that if we lower this index with an eta, this is J plus plus, and we're going to call this J plus. This is D plus psi mu plus D plus X mu. So I will have only the left here. And J minus is psi mu minus D minus X mu. So we will expand this in modes, and we will require that the modes of this current annihilate the physical states. And for the energy momentum tensor, also let me write, so there's only two independent components, which are T plus plus and T minus minus. Now, plus and minus minus here, they are both vector indices. And this is D plus X mu, d plus x plus I over 2 psi plus d plus psi plus, and well, write the indices mu. I should write one down. And t minus minus is the same with the minus. Okay, we have the action, the equations of motion, constraints. So we are ready to compute the spectrum. But then I think we need for the spectrum is the boundary conditions, right? I mean, we will have an expansion in modes also for the psi's, but we have to see what boundary conditions.
Sorry, I'm missing something.
Yes.
One index there.
Which one has only one index? J? No, it has two here. This psi mu is psi mu, so it's a vector, psi mu minus psi mu plus. So now I'm writing here, this is in matrix form, and now I'm writing each of the components of this. And these are matrices, right? These are 2 by 2 matrices. So, yeah. I know, it gets confusing, but it makes sense because psi plus depends on sigma plus and psi minus. I don't know, I can use colors if you want for the... Let's see if I will be consistent. So this plus, the pink is Pinot index. And well, here I, just by definition, well, if you don't want, so... Okay, better now. Yeah, I know, I mean, but you're right, it's very important to distinguish both. They're not the same thing. The vector and the Majorana spinor have the same number of components in 2 dimensions, and yeah, this is useful here. Okay, so boundary conditions. How do we get the boundary conditions? For the open string, so I'm going to do open superstring. I mean, both for the closed and the open, it was easy because we understood the x's as embedding coordinates, and in the open, I mean, we know a string, it has Newman or Dirichlet boundary conditions. But actually, and then somebody asked whether it could have some linear combination. And one, if you forget about what the x's are, there's a way to get boundary conditions, which is to vary the action with respect to the boundary conditions and requiring that it's equal to 0. So if you do that for the x's, then you get, and you say that the two ends are not the same, you get that it has to be either Newman or Dirichlet boundary conditions. So now we do the same for the, already, the action is there. So we'll do the same for the psi part of the action, because for the x's it's the same as before. So same as for bosonic string. So the expansion of the x's is exactly the same. So the ones that we want to expand are the psi's. And if you do that variation, what you get is, so you get an integral over d tau. So now, the boundary of the open string, psi plus, delta psi plus. And then, yeah, I didn't say it, but these are anti-commuting. Okay, I'll write it. So this at sigma equals pi minus the same thing at sigma equals 0, right? The two boundaries. So yeah, I didn't say. So you can go back to the beginning, and classically these are Grassmannian, so psi mu. Okay, another notation horrible. Well, I can put plus minus psi mu plus minus is equal to 0. Classically, they commute. The anti-commute. And because they anti-commute, you get this minus. This minus sign. So now, since sigma equals pi and sigma equals 0 are two different boundaries, then each of these terms has to vanish separately. So I have to choose psi plus equals to psi minus at each end, but this is quadratic in psi plus, and in psi minus, so I can choose, psi mu plus at tau 0 equals to plus or minus psi, and now we have these plus or minus are signs, they're not, so you will be unhappy. You want another color for 1 or minus 1. So psi mu plus at tau 0 is equal to plus minus psi mu minus at tau 0, and the same or psi mu minus at tau 0, pi equals to plus or minus psi mu minus at, the plus tau pi. And this plus, so this is free, plus or minus is not correlated to these pluses or these minuses. But actually, without loss of generality, I can choose this to be plus. And the important thing is what is the relative boundary condition that you choose. Whether you choose the same boundary condition here and here, or there's a relative minus sign. So without loss of generality, I'll write it here. So without loss of generality, I'm going to choose psi mu plus at tau 0 equals to psi mu minus at tau 0. So this is without loss of generality. And now psi mu plus at tau pi, I can choose it to be plus or minus psi mu minus at tau pi. The plus choice is called Ramon boundary condition. And is periodic in the sense that you choose the same boundary condition at 0 than at pi. And the minus sign is a Neve-Schwarz boundary condition. Or so this is R for short, and this is the NS boundary condition. And it's anti-periodic. So they will give rise to different sets of modes, and then one talks about the Ramon sector or the NS sector. So you have some open strings that have this boundary condition and open strings that have these boundary conditions, and they're not the same strings, so we see the spectrum is not the same, but you have, in the spectrum, you have everything. You have the Ramon sector and the Neve-Schwarz sector. So what's the difference? If you have these periodic boundary conditions, the modes of the expansion are integer. While if you have the anti-periodic boundary conditions, the modes are half integer. So that's so for Ramon boundary conditions, so in the R sector, psi mu minus, that depends on sigma minus, is equal to 1 over square root of 2, which you need to have all the right commutation relations. So the expansion is in the integers. The modes, unfortunately, so Polchinski uses psi mu n. Here, Becker-Schwarz use d mu n, e to the minus I n tau. So the minus depends on sigma minus. So, okay, I don't have to think. And psi mu plus is 1 over square root of 2. The modes are the same. I don't have v and d tilde because the boundary conditions mix plus and minus. Right, like in the x's that the boundary conditions mix left and right. Here the boundary conditions mix plus and minus. So I have a single set of modes. And since these are Majorana, these components have to be real. So the Majorana condition tells me that the mu minus n is the mu n conjugate. They will be operators, and as operator, one is Hermitian. So one are going to be creators, and the other are going to be annihilators. And in the Neve-Schwarz sector, it's basically the same, but expansion is in half integer modes. Sector, so Ramon boundary conditions, you have that, and with the NS boundary conditions, psi mu minus is 1 over square root of 2. That should be the same. I don't have the one. Sum over R, the half integer modes are called R, and Becker-Schwarz choose a different notation for these operators. They call them B, R. Doesn't matter the notation. The important thing is that ones are integer and the others are half integers. So with this half periodic thing, because of the 1/2 there, then you get a relative minus sign between one and the other.
Sorry, is there a factor of 2 in exponents when you, because of if sigma goes from 0 to pi,
If sigma goes to 0 to pi, there's a difference of,
it's a minus sign in the Roman sector, which is the opposite.
so at sigma equals 0, this is e to the minus ni tau. And sorry, I want that sigma equal pi. So this is e to the I n pi, and this is e to the minus I n pi. No, that's all right. Yeah.
Okay.
Yeah.
Does the value of psi at the endpoints determine on which brane the string lies?
The value of what? At the,
Of psi.
I mean, in what sense? So this will also have, if you have branes, this will also have the indices A, B bar corresponding to the branes, which branes are attached. But I'm not sure that's the question.
Yes. Would that affect the brane on which the string is lying?
Yeah, so that would be extra indices here. And you can attach both Ramon strings or NS strings to branes. So yeah, I haven't added the Champatton degrees of freedom, but if you want to keep supersymmetry, since the x's have in the spectrum, you have this extra Champatton degrees of freedom. The same is for this part of for the worksheet fermion part of the spectrum.
Once you specify the boundary condition for X,
Mm-hmm.
it is supersymmetry transformation of the take the boundary condition for the program.
I don't think so, because it's not that the Majorana is associated, sorry, the Neumann is associated to the Ramon and the so Neumann or
But if there is no relation, then the supersymmetry breaks at the boundary.
because also in the x's, so in the x's you have x left plus x right. And so the expansion is the same as this for the x's. And then you get, when you sum them, then you get, so depending on Dirichlet or Neumann, then you get, cosines or sines of sigma. So the expansion for x, but it's, I mean, because you can have Neumann boundary conditions for the and also the boundary conditions for the x's is that they are at each end. So I can choose Neumann boundary condition at one end and Dirichlet at the other. These boundary conditions are, so I fix the boundary conditions at one end, and that's without loss of generality. It's not that these are, and then what differs is whether you choose the same here or there. but it's not. Yeah, I don't know how to, in terms of supersymmetry and the boundary conditions, but you can have Neumann boundary condition for the x's, and then, so think of that as strings attached, well, or Dirichlet boundary condition in this direction. And this could be, so this let me go on and construct the spectrum, but this could be a string that is excited either with the alphas or the b's or both. So, and again, you shouldn't think of this size as embedding. I mean, the way we're thinking is there's no super space. The space is ordinary space. So these size are fields in this two-dimensional theory. So, yeah, so we don't have the interpretation as embedding coordinates of the strings for this size. At the moment I don't have a better answer. I mean, so when you do the variation, I mean, you do the variation and the x's go separate, so the action doesn't mix x and psi. So you choose boundary conditions for the x's, and then you choose boundary conditions for the psi, such that the variation of the action is 0. With respect to the boundary conditions, not with respect to supersymmetry. Okay, maybe let me think if I have a better answer to that. Yes.
Is it safe to say that because in the fermionic set we only have one derivative with respect to either sigma plus or sigma 9, once we see the boundary condition, we don't have anything about the Neumann condition, which they do actually direct, because there is no insertion of like momentum condition comes vessel or power momentum operation.
Yes, but in that, I mean, that's it. So also the Dirichlet or Neumann boundary condition mix the left and the right, and that's why you have a single set of oscillators. So I mean, in spirit, they are similar in the sense that, yeah, maybe I should try, but let me do that either in the break or later, and I can tell you this afternoon. The Neumann and Dirichlet boundary conditions, write it in terms of boundary conditions relating x left and x right. So maybe we can get some intuition from that. But these are two separate. These are two separate things. And supersymmetry is a question of the action, not at the boundary, but the action itself in the bulk. So, yes.
In the last one, the NS sector should be like exponential tau plus.
Yes, thank you. Good. Yes. Okay, let me just put in 2 minutes I'll do. The closed string is straightforward. I erase the boundary condition. I mean, I erase the variation of the action, but the variation of the action was something like psi plus d delta psi plus d psi plus minus delta psi minus d psi minus. This at sigma equals pi, 0 minus the same thing at sigma equals 0. Now in the closed string, sigma equals pi and sigma equals 0 are the same the same point. So I don't need these two to vanish separately. So then I don't need to relate psi plus and psi minus, but I can have this psi plus this psi plus here cancel with this psi plus here. So in the, maybe I erase that. So the boundary, sorry, the boundary conditions in the for closed strings are that psi plus or minus at sigma, at tau 0 are equal to, and let me put another color because this color are not related, so plus or minus psi plus minus at tau pi. So here these two are related, and this is for mu. The plus with the plus and the minus with the minus, so I don't mix plus and minus in the closed string. And I can choose either sign. So there are 4 sectors. So I have there is the Ramon, NSNS, RNS, and NSR. So here I choose Ramon boundary condition for the plus and Ramon boundary condition for the minus. Here Ramon NS boundary condition for the plus and NS boundary condition for the minus. Ramon NS and NSR. And the expansion is exactly the same expansion that you saw here, that you saw there, but with the 2 in the exponential. Now, yes, we need the 2 in the exponential. So we have R and S, and then right movers and left movers. And so psi minus, that depends on sigma minus, is the sum and no square roots of d mu n e to the minus 2in sigma minus. And this is psi plus, it's sum over n, the tilde. So now there are the d's and the d tildes, e to the minus 2in sigma plus. And in the ns sector, I sum over r. So in the r sector, I sum over n, and in the ns sector, I sum over r. So that's the way to remember. R goes with n, and n goes with r. But yeah, I guess we're more used to using n for integers and r for half integers. And these modes are b mu r e to the minus 2in sigma minus. And here, psi plus equals the sum over r. Sorry, b tilde mu r e to the minus 2in sigma plus. Hopefully I didn't make any mistakes. Plus and minus, yeah, here is a mistake. Instead of an n, this should be an r. Okay. Okay, 5 minutes break, and then we quantize. Okay, the boundary condition for the open string, sorry, for the closed string was a bit fast because I saw people wanted to go for a break. So I wrote here, for example, NS boundary conditions means we choose, so NS is the anti-periodic, so there's a minus sign between, so it's psi plus with psi plus and with a minus sign because NS, and psi minus with psi minus. So that's always the case in the closed strings. You don't mix, the boundary conditions don't mix plus and minus. And NS means that you're choosing a minus sign in both. And for example, NSR, you choose a minus in the NS sector. So in the, sorry, you choose a minus. So the NS sector is choosing a minus, and plus means it's left movers. And I put, yeah, so I try to put NS, the left on the left and the right on the right, but that's not usually the case. Sometimes in many books, I think including Becker Schwartz, the way it's written, this is right, and this is what you do on the right, and this is what you do on the left. But here, so I put, so NS boundary conditions on the left movers, so the psi plus, and Ramon boundary conditions on the other, and this is wrong. I want you to understand, and then I write the signs wrong. So again, the pluses with the pluses and the minus with the minuses, and the sign depends on whether you do an S or R. Okay, is it more clear now? And it's very different than the open string. They are called NS and R because R is periodic and NS is anti-periodic. But in the closed string, you relate plus and plus, and in the open string, you relate plus with minus. Well, and I didn't write RNS and RR, but from here you understand. Okay, quantization, easy. Again, first quantization. So the alphas are the same. So remember, I'm talking about the x's, but the x's are always there, and we have their modes are the alphas, and they have the same commutation relation we've been writing. And then the b's and the d's will have, so the b's are the ones that have an R, B, U, S. Sorry, I forgot here the M, important. In the commutation relation of the alphas, there is an M, while in the commutation relation of the b's and the d's, there is no thing. So this is just eta mu nu and delta R plus S 0. So they all anti-commute except the BR and the B minus R. And the same for the D's, D mu N, D nu M, is an eta mu nu, and a delta M plus M 0. And all the rest, so alpha with D commute, and B with D anti-commute. And the same with the tildes, right? I don't have to write, so it's, you put a tilde everywhere, and it's the same, and then the B's and the B tildes anti-commute. And these anti-commutation relations are such that psi plus minus of, let me write of sigma, tau sigma psi plus minus tau sigma prime is equal to pi, so mu and nu is equal to pi eta mu nu, and a delta of sigma minus sigma prime. Only the plus and the minus with the minus, so these signs are correlated. Okay, so how do we construct a spectrum? It's like in the bosonic string. We start from a ground state and we act with creation operators. So let's start with the open superstring. So we start with here, and here we have to, so we have to say whether we start from the ground state in one sector or the other. And then we act with alpha mu1 up to mu I minus n1 minus ni. And if you are in the Ramon sector, then you act with D. These are the ones that have integer index, minus m1, mu1, D minus, minus mj, nu j. And if you are in the NS sector, you have the alphas and the b's. I don't have to. And in the closed string, again, you have the four sectors. So you have the alphas, and then if you are in the Ramon sector, sorry, alpha and alpha tildes, D and D tildes. So this is in the RR. These and B tildes. So this is RNS. B's and D tildes in the NSR, or B's and B tildes in the NSNS sector. Yes.
Are the vacuums for the two sectors in general different?
Yeah, exactly. We'll see that. Did you know about it, or you're very good? They are very different. We'll see that. So this NS or this Ramon. So let's see what they are. So these are annihilated by alpha mu m. So either NS or Ramon. So for all m greater than 0, alpha 0 gives me p mu. So alpha 0 mu on either vacuum, or the ground state, is proportional. So alpha prime, I always get these factors wrong, but this is proportional to P mu on 0 in S, 0 Ramon. Now, if we are in the NS sector, these are the B's, B mu R on 0 NS is equal to 0 for all R greater than 0. While if you are in the Ramon sector, the mu n 0 Ramon is equal to 0 for all n greater than 0. Well, I wrote it m before. For all m greater than 0. And there's an immediate question. Here, the first is B1 half annihilates. But what happens with D mu 0, Ramon? Does it annihilate? Does it give me P mu? What does it do? Can it annihilate the Ramon vacuum? You have the answer right there. It cannot, right? Because if I act with a second B, the second, D. If I act with a second D, then they should anti-commute and give me just the eta. So this cannot be 0. So cannot be 0. And furthermore, D0 and D0. So it's in the alphas, I have the M, so alpha 0 and alpha 0 commute. But here I don't have the M, so D0 and D0, they have a non-trivial anti-commutator, which is eta mu nu. And after you saw a whole class on this, you should recognize this algebra. So this is a Clifford algebra. Up to a factor of 2, but you can reabsorb. So this means that these D0 are like gamma matrices, but in space-time. So D0 mu is, I can put equal to, and now I call them gamma and B gamma, because these are Dirac matrices up to a factor of, so I have to put a square root of 2, right? So divided by the square root of 2 or factor. The important thing is that it's a gamma, it's like a gamma matrix. So if I act, so this means that this should be in a representation of the Clifford algebra in space-time. Or in other words, this Ramon ground state is a space-time spinor. So the vacua are very different, the ground states are very different. This 0R is a space-time spinor. So that's how space-time spinors appear in the RNS formulation, which is what we wanted, right? We wanted space-time spinors. Why do I care about worldsheet spinors? The electron is a space-time spinor. Well, this is how they appear. This spinor, space-time spinor, so it's a 10D spinor. So it has 2 to the 5 degrees of freedom, which is 32, right? And it's Majorana, because everything, the psi's are Majorana. So these are real degrees of freedom, because psi is Majorana. But not Weyl, or not for the time being. So again, in 10 dimensions, one can impose Majorana-Weyl conditions at the same time, but this is Majorana, it's not Weyl. Yes? Yeah, so I haven't, I mean, we could do this in D dimensions and then D will be, but yeah, it's the same. If you do things properly with ghosts, so yeah, I'm going to say that a little bit. You get that D is equal to 10 is a dimension, the critical dimension. So anticipate. Okay, maybe as an aside, the central charge, so the C of an X mu, a boson, a free boson, is equal to 1, and the central charge of a free fermion is 1/2. And so if we have these two, then the central charge is 3D over 2. And the ghosts, so the ghosts are BC for the, beta gamma for the bosons and BC for the fermions. So the ghosts have minus 15 of central charge. So this is what gives, if you do proper thing, this is what gives D equals 10. And this will also give the nice A, such that we'll have massless vectors and spinors. Okay, so this part is the part I didn't explain for the bosonic string, and I'm not going to explain for the, because you want the total central charge to be 0.
Sorry, I cannot see why it's Majorana and not direct.
Why is Majorana not Weyl? So it will eventually be Weyl, but the way we're doing it, you're doing the same. Yeah, you will say because it's the open string and the psi plus and minus are related, then, I mean, at the end of the day, it will be Weyl, but let's, for the time being, it's not Weyl because, yeah, because in the, yeah, I guess it's not so straightforward to see that this is Majorana. It's easier to believe. To see that in principle this is not Weyl, that's less straightforward. But I mean, that's what it is, and again, eventually it will be Weyl. So now, if we build a spectrum, if we come here. So let's look at the open string. Now, from the point of view of space-time, all these are vector indices, right? Both the alphas and the b's, so both these alphas, b's, from the point of view of space-time, they're all vector indices, which means that, so 0 is a non-degenerate vacuum, is a single, it's a single state, it's a space-time scalar. While this is a space-time fermion, and this means that this will be all fermions or spinors, and this will be all bosons. So in the all the tower in the Ramon sector, we get all fermions with different spins. So 1/2, 3/2 fermions, and the NS sector, they are all bosons. And in the closed string, you have RR, NSR, RNS, and NSNS. NSNS are obviously bosons. RNS and NSR are fermions. And this is fermion and fermion, so these are bosons as well. And everything is space-time, right? This is, I'm talking now about space-time. Which formula? The 3D over 2 or the minus 15. From having D, so dx is, each x has central charge x, each free boson in 2 dimensions has central charge 1. And this you have to be, this you have to believe me as well. I didn't enter into the details of CFT. Every free fermion has 1/2. So if you have D of them, then it's D plus D over 2. So this is a 3D over 2. And the Gauss, believe me, is minus 15. Yeah.
So why is the NS sector of bosons? Because we have the same algebra as D, right?
Yeah, but there is no zero mode for the B's. That's a difference. Yeah, that's a big difference. That the B's annihilate, all the positive annihilate the. Okay, so let me write the conditions that the physical states, we know the physical states, the sandwich of the modes of the energy momentum tensor. So now physical states should satisfy. So the constraints that the energy momentum tensor and the supercurrent have to be 0, turn into phi Lm phi equals 0 for all m greater than 0. And phi equals 0 for all n greater than Cm. And I'm going to tell you, so these are the modes of the supercurrent. I will write them. And not for only for the positive. Sorry, for any, yeah, you're right. Once I put it, yeah, sorry. Because the minus m are the daggers, so they act on this. Yeah, sorry, thanks. So this is for all m, but different from 0 because it's a story of the normal ordering thing. So these are the modes of the supercurrent that I will write. These are the ones in the Ramon sector, and these are the ones in the NS sector. So let me write, so the LMs, which are the modes of the energy momentum tensor, so you can obtain them integrating over sigma. So the L's are the T++ and the L tildes will be the T minus minus e to the IM sigma T++. And what we get is this, the same as before for the alphas. Alpha minus n, alpha m plus n. And something I could have put to avoid this L0 and L0 hat definition is this normal ordering, which means annihilators, I put the annihilators always to the right. So this means annihilators to the right. And this takes care, so this is the thing without this 0-point energy, without the commutators. You just put annihilators on the right and forget about the fact that they have a non-zero commutator. So that's the part of the alphas. And then the part of the psis is 1/2 of the sum of R in C plus 1/2 of B minus R, BR, BR, R plus M plus R, sorry, it's a bit small, normal order. And again, there's always a contraction, mu and mu. So this is for the NS sector, and for the Ramon sector is 1/2 of the sum over n of the mu minus n, or let me not put the mu, the m plus n, normal order. No, sorry, I'm forgetting, sorry. No. I mean, I'm forgetting very important factors. Sorry. Well, this is not correct. So plus 1/2 of the sum over R of, sorry, R plus M over 2. Yeah, otherwise you don't get the same. Oh, very important, sorry about that. And this is n plus M over 2. Sorry, I was forgetting these factors. Here there is no factor, and here there are these factors. And I write the modes of the supercurrent, and then we continue this afternoon building the spectrum. So in the NS sector, in the Ramon sector, these modes are Fm, and it's, I don't know, for some reason, these are the good factors to have the thing simpler. So e to the I m sigma plus, so I have to integrate this current, say, that had 2 plus indices, one white and one pink. And this is the sum over n of alpha minus n dm plus n. And I put normal ordering. So n alpha and the d, right? Because this mixes the x's and the psi's. And the GR which is the sum over n. So you sum over the integers also for this. And this is the alpha minus n and br plus n. Always a contraction with mu. And you have the same thing with the tildes. So all the same with the tildes if you are in the closed string and there is the right moving sector is independent from the left moving. Yes.
When we have the oscillator in second supersymmetric current, do we have to sum over Z or
Yeah, we sum over C. So the half integer thing is in the modes. The modes are half integer, but you sum over n, yeah. Integers, yeah.
Sorry, Mariana has clarity about why we're calling the fermions as ghosts. I know ghosts are the fields that appear when you try to integrate out some internal gauge. So what is the freedom you're trying to integrate out here to appear?
It's the conformal transformations that the leftover conformal transformations that you are, which is, you have the conformal transformations also in the super. So this is a super conformal field theory. And in the bosonic case, you have the beta gamma. No, I always forget. It's the BC, which are anti-commuting, and for the psis, you have beta gamma, which are the commuting system, and so you have the ghost and their sort of super partners. Okay, no, yeah.
Why you write n plus n over 2? Not n
Here, yeah, so you need to, because this is the right thing that will count the oscillator number, because the difference, the alpha m and alpha n, they have an m here, while the b's, and the delta m plus n 0, while the b's don't have b, I don't know, br, bs, this is a delta r plus s 0. So that's why in one case you don't get dm, and in the other case you do. From the T++, this is because, so T++ is d plus x, d plus x. So the 1 over n that you have in the expansion goes away, and then it's psi, d psi. And here you didn't have a 1 over n, but in this is this derivative that will bring this factor there. You can do it. Do this integral. I gave you the expression for T++, and you'll see that, that's what you get. Okay, so I'm here for the question and answer session if you have more questions, and then we continue and finish this afternoon. Thank you.